Something peculiar is unfolding on the surface of Betelgeuse, the red supergiant in the Orion constellation nearing the end of its life cycle. The star grabbed headlines back in December 2019 when it unexpectedly started to dim, reaching an unprecedented low in brightness. By February 2020, a phenomenon later dubbed the Great Dimming of Betelgeuse occurred. Although it eventually returned to its usual luminosity later that year, this event piqued astronomers' interest, leading them to aim some of the most advanced telescopes toward it for a closer examination. What they uncovered was truly remarkable. Betelgeuse's surface is in a state of agitation, generating a cosmic spectacle. Betelgeuse holds significant importance. It stands as one of the most captivating stars visible in the night sky. Originating from a stellar nebula, Betelgeuse spent around 90% of its life in the main sequence phase, where it converted hydrogen into helium in its core. However, due to its substantial mass, approximately 15 times that of the Sun, it charted a different evolutionary course. Instead of transitioning into a red giant like typical Sun-like stars, it transformed into a red supergiant. Astronomers are particularly drawn to Betelgeuse because witnessing a star in its ultimate phase of evolution with a naked eye is a rare occurrence. This makes it a valuable laboratory for understanding the processes that precede one of the most violent stellar events, a supernova. The last significant supernova observed in the Milky Way was Kepler's supernova in 1604. Since then, no other supernova has been observed in our galaxy within the naked eye limit. So, naturally, anything that happens to Betelgeuse is a big deal. Even as Betelgeuse's brightness diminished, astronomers speculated that this behavior might be a precursor to an impending supernova explosion. To investigate further, they used the Atacama Large Millimeter-Submillimeter Array, ALMA, to closely monitor the supergiant. Observations from ALMA revealed that the dying star appears to be spinning rapidly, with speeds exceeding those predicted by current laws of physics. This was confusing. Why does Betelgeuse seem to be spinning faster than any other star of its age? Is this seemingly rapid rotation a sign of the impending supernova? Just as the explosive event of a supernova like Betelgeuse triggers a cascade of cosmic reactions, the initial indication of Betelgeuse's unusual behavior emerged from ALMA's surface radial velocity map, which visually depicts the speed at which different parts of celestial objects move toward or away from an observer. ALMA's observations unveiled a striking pattern. One half of Betelgeuse's visible surface exhibited a blue shift, indicating motion towards us, while the other half showed a red shift, indicating motion away from us. This insight was pivotal in accurately gauging the star's rotational velocity. Comparison with data from the Hubble Space Telescope further affirmed that Betelgeuse was spinning at a notably brisk pace. Various hypotheses have been proposed to explain this rapid rotation, with one suggesting that Betelgeuse may have once been part of a binary system, absorbing a companion star in a process colloquially termed celestial cannibalism. While such occurrences are not uncommon, there is no conclusive evidence of this phenomenon among red supergiants like Betelgeuse. However, if Betelgeuse evolved as a solitary star, its unexpectedly high rotational speed poses a puzzle. To appreciate the significance of this anomaly, it's essential to grasp the sheer magnitude of Betelgeuse. This red supergiant is 15 times more massive and approximately 1,000 times larger in diameter than our Sun. If Betelgeuse occupied the Sun's position, its expanse would encompass Earth and extend beyond Jupiter's orbit. Furthermore, Betelgeuse has transitioned from its main sequence phase, evolving into a red supergiant. As stars like Betelgeuse age and cool, they expand. According to the principle of conservation of angular momentum, this expansion should cause their rotation to slow down. Additionally, they lose mass through stellar winds, which also contributes to a decrease in their rotational speed. Current theory suggests that red giants should rotate at speeds around 1 km per second, and red supergiants like Betelgeuse at even slower speeds, typically less than 0.1 km per second. Yet, Betelgeuse defies these expectations by rotating at about 5 km per second, which is 50 times faster than what is typical for stars in its category. To solve the mystery of Betelgeuse's unexpectedly high rotation speed, astronomers had to confirm whether the rotation they observed was real or just an error in measurement. They considered the possibility that other activities on the star's surface could be misleadingly interpreted as rotational movement. To delve deeper into this issue, astronomers utilized the ALMA telescope, which comprises 66 individual antennas of various sizes and is one of the most advanced radio telescopes in operation today. Using ALMA's capability to observe submillimeter wavelengths of light, astronomers examined the hot gas in Betelgeuse's outer atmosphere. The researchers aimed to find out if Betelgeuse's rapid rotation was actually being mistaken for something else happening on its surface. They suggested that what might be going on is a process called convective flow, which is how stars like Betelgeuse move heat around. In convection, hot material rises to the star's surface because it's lighter, while cooler, heavier material sinks. This creates big swirling patterns known as convective cells that look like giant boiling bubbles. These patterns can extend from the star's outer layer deep toward its core. The team theorized that these boiling bubbles might be creating an illusion of rotation, with one group of bubbles rising on one side of the surface and another group sinking on the opposite side, making it look like the star is spinning by causing some parts to come towards us while others move away. This movement could explain the blue-shifted and red-shifted regions observed in ALMA's maps. To test their idea, the researchers created a computer model of a non-spinning red supergiant star with a boiling surface, just like Betelgeuse. They compared the model's behavior with actual observations from the ALMA telescope. Surprisingly, the simulated star and the real observations matched up perfectly. This confirmed their theory that it's not the fast spinning we're seeing on Betelgeuse, but instead its surface bubbling up like a pot of boiling water. This bubbling effect is so strong that even the most advanced telescopes can't tell the difference between this and the star actually spinning. The study provides more evidence of Betelgeuse's unpredictable behavior, which isn't a new phenomenon for astronomers. In the past, Betelgeuse has been at the center of surprising events. For instance, the Great Dimming episode almost 4 years ago was finally explained by the theory that the star had expelled a large amount of hot gas. As this gas cooled outside the star, it formed dust that temporarily blocked some of the supergiant's light, making it appear dimmer from Earth. In 2023, Betelgeuse showed another strange behavior. Its brightness increased by about 50%. Initially, astronomers thought this might be a precursor to a supernova explosion. However, further analysis revealed that this was actually a lingering effect of the 2020 Great Dimming. The massive release of dust and gas during that event disrupted Betelgeuse's normal cycles of brightness, which usually include cycles lasting 400 days, 185 days, 230 days, and even as long as 2,100 days. The disturbance from the Great Dimming specifically altered the 400-day cycle, shortening it to just 200 days and causing an unexpected increase in brightness. Predicting when Betelgeuse will undergo a supernova is a challenging endeavor due to the difficulty in pinpointing its precise stage within the stellar life cycle. Scientists must discern whether Betelgeuse is currently undergoing helium burning or carbon burning. The timing of the supernova event hinges largely upon this determination. Positioned 550 light-years away, we occupy an optimal vantage point to potentially witness this extraordinary cosmic event. Upon the occurrence of a supernova, the initial indicator would likely be a surge of neutrinos, minute particles emitted in abundance during such explosions. The Supernova Early Warning System, SNEWS, utilizes a network of neutrino detectors to detect these early signals. Subsequent to the neutrino burst, a supernova would emit an immense amount of energy, resulting in a brightness that could make it visible even during daylight for a period of approximately 2 to 3 months before gradually dimming. While a Betelgeuse supernova would offer a spectacular display and pose no threat from its considerable distance, it would leave a discernible alteration in our night sky. Betelgeuse serves as one of the shoulders in the constellation of Orion, and its absence would render Orion seemingly missing a shoulder, with the remnants of the explosion not perceptible to the naked eye. Many inquire whether we can leverage the James Webb Space Telescope to study Betelgeuse and forecast its supernova accurately. However, the answer is negative. Although the James Webb Space Telescope boasts considerable power, it is unsuitable for observing Betelgeuse. The telescope is designed to scrutinize distant and faint celestial objects, whereas Betelgeuse's brightness exceeds the sensitivity range of JWST detectors by approximately 1,500 times, rendering it unsuitable for accurately predicting the star's evolution stage. If you enjoyed this video, be sure to give it a thumbs up, share it with your friends, and subscribe to my channel for more content like this. Thanks for watching.